So some questions that are commonly asked on social media are, how can I get started with Arduino? Or I've done the starter kit, now what? So hi, my name's Glenn and welcome to All About Arduino. In this series of videos, I attempt to answer those questions by giving some follow-along examples. So in this second video, I'm going to build upon what I did in the first video, and we'll learn about some techniques to ease your programming life, and also a technique to allow you to connect more stuff to the Arduino than you actually have I/O pins available. And as before, we're going to be working towards a fully functional dice game that you can use to actually play games with. So if you find this video helpful, don't forget to like this video, subscribe to my channel, turn on the notifications so you'll see new content as I release it, and also leave a comment. I do like to hear how you're going. And so also look for me on social media. I'm often on Reddit in the r/Arduino subreddit, or you can look for a list of my projects on my website. Okay, let's get going. Okay, so this is the second lesson where we'll look at expanding our I/Os by using some external supporting hardware, specifically a shift register chip. But before we do that, I'll just go through the process just quickly. So I recommend, if you do have the starter kit, just follow the examples in that, learn some basic concepts, then change it and adapt it, and then merge a couple of examples, rather like we did in the first video, which if you haven't seen that, I'll put the link in a video description. So definitely go through that first, because we'll reuse some of the stuff from that in this lesson. And then another thing that's helpful if you are wanting to learn is to have a project goal. So this video will build this dice game, which again I showed in the first video just how it works, so refer to that if you want to see what that does. But by having a project goal like this, it sort of focuses our learning. So the buttons, the LEDs, and since we have so many of them, we need to have some additional support because it's too many to connect. So these shift registers, which is the topic of today's lesson. And of course, if you ever get stuck, by all means, just seek advice. Google's a great resource. I'm on Reddit a lot, but there's also lots of other forums where people can help answer questions and solve particular problems that you have. Okay, so in the previous lesson, we looked at the basic examples that many starter kits have, and then we adapted them and changed them and merged them, and I left 2 challenges for you to try, which I'll present my solutions in this video. This lesson is about expanding the I/Os, and in the first lesson I taught some programming techniques that makes your life easier, so I'm going to introduce some more programming techniques here. In particular, trying to sort of take some of the hard coding out and use data to drive the program. And then of course is the final project. That's on Patreon, which is to actually build the entire project. If you don't want to go to Patreon, you don't need to. There's enough information in these first 2 lessons for you to build this completely. But what I will show is some additional techniques for programming, again, all oriented to making your life and your journey in Arduino and programming a bit easier. Also, you might not be interested in building this project. That's fine. You might want to do other things. This first 2 videos are still quite useful to you though, because even if you don't want to build this dice game, but you want to do something else, the techniques that I teach in these are basically portable to other projects. They're more about foundational concepts and ideas, again, to make life easier for you and get a good working project. So you can learn the basics, as if you like, so what to do next after the starter kit, and then move on to your project using some of the techniques that I showed in the previous video and this one. So as before, there's a bill of materials that you need to complete the projects. We're doing part 2, the shift register. So you need an Uno, a breadboard, 8 LEDs, 8 current limiting resistors, because we always need a current limiting resistor with our LED, and 1 shift register. Now most starter kits will come with a shift register, but if it didn't, you can easily get them at a nearby electronics store or any one of the multitude of online parts providers. Okay, so let's have a look at the challenges. So I left you with 2 last time, and one was to blink a bunch of different LEDs at different rates, and the second one was to add a second button and then just blink one of the LEDs at different rates. So one of the approaches that I can take to solving this problem is to replicate the code, which is what we did when we blinked the second LED. But I'm going to introduce a new technique called arrays. We'll use this quite extensively throughout this and the following lessons. And the thing that arrays lets us do is it's a first step to sort of taking data out of the program and sort of separating it out of the actual code. So let's have a look first of all what an array is, and then we'll look at how to use it in the first challenge, which is the blinking of the LEDs. So I'll use an analogy. An array is a mechanism that places similar values into a box. So if we go to sort of use an analogy of going to the supermarket, you can just get a bunch of cans from the supermarket and they're all just sort of loose and lying around and they're sort of a little bit awkward to use. But if we put them into a box, then it's much easier to process them. And so an array is kind of like that, collecting some like things and putting them into a box that we can sort of use as one go. Later on in lesson 3, I'll look at a concept called a struct. And so a struct is a bit more like a gift box, where an array, you kind of have similar things in a box, so it's like a 6-pack of the cans. Whereas a struct is more like a gift box because we can have one can of one thing and something else, maybe some chips or something like that. So different things put into a single unit, and then we can actually create an array out of those as well, so we can have an array of struct. Now, how does an array work? So an array has an index. So you might say that this is the first can, this is the second can, this is the third can, this is the fourth can, this is the fifth can, this is the sixth can in the box. So that's the index. But in programming, most modern languages, the indexes start at 0. So it doesn't matter really where you start. We could start here, we could start here, we could start here. It doesn't matter which direction you go. But the way the index works is as an offset into the box or an offset into the array to identify a particular element. Now, as I said, it starts at 0. So the idea is that whatever your starting point is, let's say it's here, that you want to offset it by that index value. So if we want to get this can, then we're offsetting from the start 0 elements. So that's this one. If we offset one element, then we're skipping over this can and then going to the next one. If we offset by 2, then it's this one. If we offset by 3, according to the counting I used originally, then it would be this one. If we offset by 4, this one. And then finally 5, that would be this one. So our lowest index is 0 and our highest index is 1 less than the total number of objects in the box. So if you imagine that these two didn't exist, then we'd have 0, 1, 2 and 3. Okay, so hopefully that makes sense. Now, what is a similar value? So we'll look at that in the code, but for example, I might create an array of the pins that the LEDs are connected to. Similarly, I might create an array of the previous time that we checked its state, stuff like that. So this is the program that I had when I left you with the 2 LEDs blinking. As you can see, we've replicated the code. Before I get into this, I'll just briefly look at the circuit. So for the first challenge with the 4 LEDs, ignore these ones over here for now. I'll use those in the second challenge. But we have these 4 LEDs. There's nothing really different between this and what we had previously, other than I've made it a little bit tidier and a bit more organized. But as you can see here, we've got the current limiting resistors, which I've used 470 ohms. I've got these LEDs with the short leg connected into the resistor, which connects to ground. And then finally from the cathode side of the anode side of the LED, that's connecting to these GPIO pins via the orange wires. So as you can see, I've connected them 13, 12, 11 and 10, or if you prefer 10, 11, 12 and 13. Again, these yellow wires are for the buttons, which I'll use in this next challenge. Okay, so that's exactly the same circuit as before. Nothing terribly exciting there, except there's just now 4 of them and it's a little bit neater and tidier than before. The other difference is that I've got the power coming in over here. Yeah, so again, I've got the power connected. I'll need the plus V for the buttons later on. It's not being used for LEDs, but because I've connected the resistors on this side to use shorter wires and also not having to jump over the the LEDs and just make the whole thing a bit tidier, I've organized it this way. So that means I need to connect the ground on this side to the ground on this side, because remember, these are connected all the way along these edges, but they don't connect across the channel here. And also these don't connect to these interior ones, which is why I need to use these wires and resistors here. Okay, so let's look at the code. Now, as I said in the intro, I could just take this and replicate it, and then change all of these numbers to 2 and 3 and stuff like that, but I'm not going to do that. I'm going to use an array. Now, I noticed I mentioned, in fact, in the previous video, that I'm deliberately picking 0 and 1 for these variable names to distinguish them, because those will correspond to the indexes in our array when we define it. So let's start with this, the pin mode. So we're setting all of the pins to the output. So let's create an array for this, and then use that array to set the pins to output. So where have we declared the LED pins? Here they are. So I'll just comment that out so we can compare it. So far that's the same. There's nothing special about that. But to create an array, we use these square brackets. So that indicates an array. In this case, where I just stuck a 0 onto the end of the variable name, that just becomes part of the name. But now we created a variable simply called LED pin, and inside these brackets we can insert a 0 or a 1 or a 2 later on, not here, to reference a particular element. Now here we just assigned it to LED built-in, so that part is the same. Now where we get a bit different is we have more notation that allows us to specify multiple elements. And so you have to have an open bracket, a closing bracket, and the trailing semicolon. That's a little bit different to the code, where you don't need to have a trailing semicolon for these brackets for code, but you do need one for the variable declarations. So that's an important thing to remember and often overlooked. Also, these things don't have to be on one line, so it doesn't really make much difference for this example, but I prefer to put it over on 2 lines. So then we just list them. I think those were the connections, weren't they? Yep, 10, 11, 12 and 13, which is also LED built in. And that's pretty much it. Now I think I'll just do that quickly for all of these other ones as well. Now in this case I don't particularly want to initialize it to any particular value, so I could do this. I won't. I'll initialize it like this, and I'll actually make sure that they're set to 0. Now if I didn't want to do that, again as I said, I could just declare it like that, and I will leave it like that now, and I'll actually initialize it a bit further down. But we can see here, I'm just creating here an array, and I'm specifying that it has 4 elements, so that'll be 0, 1, 2 and 3 as the indexes. In this case I didn't need to. The compiler will count how many elements there are here, and there's 4, so it will, if you like, automatically default this to 4. So in this case where I don't really care about it, I can get away with that. Now that creates a bit of a problem for us, because if I decided to add another one here later on, I will have to remember to go and update this. In lesson 3, where I use a struct to basically create if you like, a gift box. So in this case, the gift box would be a single thing that contains the LED pin, the previous millis, and the interval as a single thing. That problem would actually be solved. But for now, we'll do it like this. We'll take it one step at a time. And lastly, now in this case I do care about the values, so I will initialize them. Again, just to show you can do it on one line. Don't forget the trailing semicolon. What values did I say I was going to use? Looks like it was 150, 200, 333 and 500. Okay, so how do we use this, this structure in the code below? Okay, so what I'll do is I'll just duplicate this first, so again we have a reference point and comparison point. Now we can actually reference these elements just by hard coding the values here, but we haven't really done much, haven't achieved anything just simply by typing in these brackets around it. If anything, we've made it even more wordy. So rather than doing that, what I'll do is actually I'll use a variable. So I'm going to use a variable IDX. It's very common just to use a more simpler variable like just I, but I'll use IDX just to minimize my typing and also explain what it is. Now I'll start off with a more verbose version of how to manage this IDX, and basically want to create a loop. So first thing I'm going to need to do is create the variable, so IDX, and I'm going to initialize to 0 because that's our first index. And then what I'm going to do is I'm going to say while the index is less than 4, which is the number of elements that we have in our array, I want to run this loop. Okay, so what will happen is we'll set IDX to 0, and IDX is less than 4, so it'll definitely come into here. And so then what it'll do is replace IDX with that text with 0. So effectively it'll do LED pin 0 as output. So that's great. But the problem is IDX is going to be stuck at 0. So what we want to do is increment it. So this is a shorthand notation. You can also write like that, or you could even write IDX equals IDX plus 1, which is sort of similar to that interval calculation I used in the previous examples. This is a shorthand notation for that. This is an even more shorthand notation, and this can actually be used in other ways as well, but I'll just use this simplistic version here. So what will happen is we'll start at 0, we'll set LED pin 0 to output, we'll increment IDX to 1, then repeat this because it's still less than 4, so it'll do the same for LED pin 1. Then it'll do it for pin 2, then it'll do it for pin 3, then it'll increment, so now it's equal to 4. So 4 is not less than 4, so this loop will fall out and then come down to here. Now I can repeat that here. So again, instead of replicating all of this, what I'll do is I'll indent it, because obviously I'm going to run it in a loop soon. I'll use the shorter name, which is more commonly used, so I. Now, this structure is so excluding this one line here, this structure is a fairly common pattern. So there's what's called sugar or syntactic sugar that allows us to create this structure fairly easily. So the syntactic sugar is a for loop like that. And again, it loops around a block of code, so we need to put the block of code into a block, which is what these braces do for us, and this is the block of code that we're going to run. It's a single statement. Actually, for single statements, you don't need those braces, but it's a good habit to put them in. Now, the for loop inside its parameter list here has 3 components. One being the initializer, next being the, if you like, the condition to keep running, and then the final component being how to what to do to update the loop conditions. So I'll declare this. It's the initialization part. I equals to 0. Declare the variable as well. Now the condition is going to be while I is less than 4, because we want to keep doing this while I is less than 4. And the same thing, the loop counter is incremented as we go through. And that's pretty much it. That should do the job. So let's plug him in. I'm not sure what program's on here, but it doesn't matter because I'm going to upload this one. Now this is a new Arduino, so notice the COM port has changed. If you followed from the previous videos, that would be COM13, but that's a different one. In fact, this one from the previous video is COM13. So when you change your Arduino, your COM port can change, so you need to make sure that you select the right one. So now it's COM15. It's still an Arduino Uno, so that's fine. And then we just upload him. Okay, so it looks like we've got an error. Oh, I typed it in wrong. I also forgot the initialization part. So because I didn't initialize this here, I don't have to because it'll probably be set to 0, but I might do it in here. So I can initialize it like that rather than typing out
a long list of values here. Well, it's only 4, so it's not a big deal. But rather than typing it out, I could initialize it here if it's all to the same value. And of course, I could initialize it to anything I like. It doesn't have to be 0. I could initialize it to that if I wanted to. So I'll just leave it like that. That's going to work just as well. So we try again. And of course, if I declared my variable, index variable to be IDX, I need to use that name. I just can't randomly make up another name, even though it is a convention to use that name and hope that it works. So there we go. Now we have the LEDs blinking in a random, sort of erratic fashion. And that's just simply due to the fact that the times are not multiples of each other. You can play around with the times and have other interesting patterns going. You could add more LEDs. If you do, don't forget to add the pins here. Don't forget to add or increase the element here. And also don't forget throughout here to increase these. Now again, it's a bit of a pain to have to go and do that sort of maintenance. So in a future video, what I'll do is show you how we can create a macro where we can actually get the code to automatically adjust itself based upon the size of one of these arrays. So we can actually work out the number of elements that are in this, and I think hopefully use that there, but definitely in places here, like here, where the loop index is up to the number of elements that are in the array. That will make life easier for us when we maintain it, but I won't show you that now. That'll be something for the future. All right, so let's look at the second challenge. So I don't need that anymore. And so this is the previous program where we left the button challenge where the single button could switch the 2 speeds. Now, same principle applies. If I wanted to add another button, I could certainly replicate this code. The original code had an if statement here. So this is the original code. And you can see there's this if statement here. Now we could expand this out and have a lot more conditions here. But now that we've learned about arrays, let's see if we can use that instead of this if statement and therefore hard coding this into the program. This sort of has the same problem as before, where I was sort of saying if I wanted to change some values, like the number of elements in the array, you have to sort of step through the program and make sure those changes are applied. If you wanted to change the timings, you'd need to sort of step through this as well and make those changes. So we won't do that. We'll explore using the arrays. So start with this copy of it. I've added some comments in here just to make it a bit easier to read. I won't spend too much time on that. Okay, so where should we start? Let's start by defining our buttons. Now, I'll start actually at this, not the check blink, the check button press. Now, note that one of the things that we do here is we give it the button pin and we actually change a couple of things in here. So the last debounce time, the previous button state, and things like that. Now, a function can only return one value. So what I'm returning here is the fact that the button has been pressed or not. So that's a little bit of a problem because we do need to keep track of this, but we need to keep track of 2 of them now. When there was only one button, it was fine to have this function that did the one button. So what I could do is I could replicate this, just copy and paste that, and I could call this number 2 or faster. If I did call this one like check button press faster, then it, because it's different code, could update a different variable and things like that. But I won't do that. I'll use arrays again. So we have to sort of make a couple of little changes here to make this work. So the first thing I'll do is start with the arrays. So I'm only going to use one LED, so that's fine. Focus more on the buttons. So it's basically these 3 here that I need to modify into arrays. So I'll start by duplicating this. So again, you have something to compare it to, and then I'll comment them out. So the first thing I'm going to do is I'm going to create my array of button pins. Now just quickly look at the circuit. So as before, the LEDs are connected up like that, and I've got the 2 buttons. So this is the same circuit as before. there's a pull-up resistor which is connected to the plus V side. That goes through the button, which then on the other side of it goes to ground, except for now I've got two of them. But as before, the yellow wires, which is the tap into the button circuit, are connected to pins 2 and 3 in this case. So we've created our button pin array, and we're going to initialize it to 2 and 3, because that's where our buttons are. Now this isn't saying anything about which one's up or down, it's just saying there's a button on pin 2 and a button on pin 3. So later on I'll apply some logic that determines whether which button means up and which one means down. Now similarly for the button state, I need to make that an array. I didn't previously initialize that, but it's probably a good idea to initialize it, just to make sure we know what we have. Again, I could initialize this in my setup. Similarly for the previous button state, turn that into an array and its initial values. Again, I could initialize that in the setup. And then finally these ones. So I need to make the last debounce time equal to an array. And again, I'm going to have two values. Again, I could initialize this in the setup. And now this one, I don't need to make it into an array. So I might actually remove, well, actually I know I'll leave that so it's the same. And yes, that's the same. Because the delay is sort of like a global thing. The debounce delay is 50 milliseconds. Unless you need to have different values for the different buttons, which is unlikely, you could just reuse the same value. So it's a bit like when we got the current time. We could use the one current time to determine if it's time to blink an LED. We only need one debounce parameter to manage the debounce processing. So that one's fine to leave by itself. Alright, so now we've created these arrays. Next thing we need to do is to look at this. Now instead of passing it a button pin, what we need to do is pass it a button index. Now I don't have to change the name, but it's going to make it a lot less confusing, I think, if I do. So instead of calling it button pin, I'm going to call it button index, meaning the index into the array. So now I just have to use that index throughout. So button pin at button index. Again, if I wanted to, I could have called this thing I, if I wanted to. It's not terribly meaningful in this context, so I think I prefer to use the full name, or I could have called it IDX. Any of those names is fine. It's best to use a meaningful name if you can, because that then, if you generate a documentation from this, it would use a proper name. So I'll keep it at index. So I'm only processing one button on each one of these calls, so one reading is fine, but I do need to index these things that I've remembered. So that one, the last debounce time, and the previous button state. Oh no, this one. We only have 1 millis, so the one time is fine. Plus we've already talked about this. We only need one of those. We're only dealing with one, so the reading is fine, but the current button state needs to be indexed, as does that and that. And that should be good enough now. Now in terms of setup, we can do the same thing. I can use this for loop or the while loop, it's up to you. I tend to use this because it's much more convenient. Now, I was just going on about using a proper name. So in this, we're declaring a reusable function. So it's a good idea to sort of declare what the parameters are with meaningful names. As I said, I could use I, but if you're going to copy and paste this into another program later on, it's much better to use a proper name here, because then you can sort of understand what it's meant to be. So in this case here, it's just the life of the index is only for here. It has no meaning beyond this these 3 lines of code. So having a simple name for convenience is good enough, because we're focused more on what the values are that's being provided. And then a little bit further down is the loop. So again, I'm going to set up a for loop. Now, because in this case, it's going to be a little bit more complicated code, I'm going to use a proper name. I could get away with using I again if I wanted to. So it really depends upon you, but in this case I'd prefer to use a proper name so I can be clear on what it is I'm referring to. Okay, so that's our loop. It steps through both of the buttons. So this is where I'm going to check for the button press. So the first thing I'm going to do is basically this. So I'll move that up here first. Again, I should indent it to show that it's under the control of this for to make it very clear. Now in this case, this is where I need to pass the index. So the index is our counter for this loop. So I want to check button 0 and I want to check button 1 to see what happens. As before, this returns true if the button is pressed. So with button 0 or button 1, it's pressed. So if the button is pressed, the next thing I need to do is work out, well, which one was it? So I need to do something like this. If button equals 0, then let's call that, I don't know, slower. Now I could simply get away here with else because there's only two options. There's button 0 and button 1. But if there was more buttons, I don't know what they'd do, then I would do another if there, so an else if. So we'll say this is faster. So this is the button that says go faster. Now I'm going to need another global variable. So I'm going to create another index. So I forgot to create an array here of the intervals for the speeds. So I'll just do that now quickly, and then it'll be clear why I need another index. I'll duplicate that line. Now in this case, I'm not going to do that calculation, so I don't need it to be a variable value. And because I'm going to have intervals, I'm going to declare it as a plural. Some people don't like that. Okay, so what did I say my intervals are going to be? They'll do. And of course, I don't need this anymore. Now there's only one LED, so these are fine as so-called scalar variables. They're not an array, so it's an array or it's a scalar. So these are fine because there's only one LED, but I do have 4 intervals now, so I do need that to be in an array. And then, of course, I need to have an index to track which one of those I'm currently using. So I'll start off with the 0th element, so that would be this one. Does it have to be unsigned? No, it doesn't. I'm never going to have a negative index, so I prefer to do that. As you can see, the number increases as our index increases. So the 0th one is basically going to be an interval of 150 milliseconds, and the third one, or the 4th one, which is index 3, will be 750 milliseconds. So as our index increases, we go slower. Conversely, as our index decreases, we go faster. So in this case, we want to increase the index. And in this case, we want to decrease the index. So just like this plus plus increases the value, this minus minus will decrease it. And we could also write that using this notation. These are all the same, but obviously this one is a much simpler way of doing it. Now there's a problem with this in that what happens when we reach our limit? So again, going slower, element number 3 was the slowest one. But this has no bounds. It just keeps going. Each time we keep pressing it, it will go 3, then 4, then 5, then 6, then 7. That's going to be a problem. Similarly with this one, interval index minus minus, we start at 2, then it goes to 1, then 0, then -1, then -2, -3. I did declare it as unsigned, so it wouldn't actually be interpreted as -1. It gets interpreted as something else. But either way, that's a problem. So we need to put some constraint on it. Right, so what I'm simply going to do is I'm going to put this under the control of an if. So interval IDX is less than 3. Now note I'm using 3 here, not 4. then I'll increment it. So what that means is if interval in IDX is, for example, 2, then I can increment it. Then it'll be 3. But if I push it again, interval IDX is already 3, so this won't execute because it's 3 is not less than 3. It's equal to 3. So this won't execute. So basically that puts an upper bound on it. Now I can do the same thing here, well, a similar thing. So if interval IDX is greater than 0, and I have to get our block right, then I'll decrement it. So what that means is when it's, for example, 2, that's greater than 0, so I'll decrement it to 1. Next time if I press it again, 1 is still greater than 0, so I can decrement it, and then it'll become 0. And at this point here, when it's 0, it's no longer greater than 0, so therefore this won't happen. So these if statements effectively put a barrier on how far it can go. So the final thing I need to do here is apply the index. And so when we check whether it's time to blink or not, we'll use the appropriate index. Now again, note how convenient this is, because I know I have a check blink function that can take the pin, the previous time, and some interval. So I don't really care how that works. I don't really care about how I edit that code. I can just pass the values without remembering the detail of how it works. Of course, the detail is up here. We can actually see how it works. But instead of having a huge lump of code here that's, well, basically this, it's much cleaner. So I can just check whether it's time to blink the LED by giving it the pin number, the previous time, and whatever the current interval happens to be. And that current interval is determined by this logic up here, which determines whether I've pressed a go faster or go slower. All right, so let's give it a try. So I renamed the index so it would be plural. Sorry, the intervals array so it would be plural. So we'll give that a try. If you rewind the video and look at the actual error message, it does actually suggest that. You can't always rely on its suggestions, but it sometimes does provide a helpful suggestion. Okay, so now as we can see, we have just the one LED blinking, and it's blinking fairly quickly, which means that its interval is currently this 150, which is what we expect because we start at 0. Now if I press this one, I can't remember which one was go slower. I think this one was, this one's go slower. So that's incremented the index by 1, and so now we're going a bit slower. Press it again, it's even slower. Press it again, and it's even slower, even though it's a bit hard to see. But if I keep pressing it, it's not going to change from that. It's stuck at that speed. So this one hopefully will be the go faster one. So I push it once. It looks like it's blinking a bit faster. Push it again, it's faster again. And then that's the original speed. And again, if I keep pushing this, it won't go any faster. But I can go down part way and then up and then down again and to the slowest value. So both are active when it's sort of in the middle. Okay, so that's the challenges. How did you go with yours? It'd be interesting to see how you went in the comments, or even make a post on Reddit and let me know that you've done so. I'd like to see your approach and your solution if you did have a go at it. Okay, so let's start the main topic of this video, which is about looking at shift registers. And shift registers are a great way where we can expand the I/O capabilities of our MCU. If you look at the final DICE project, that's going to use 40 LEDs. And we actually don't have that many GPIO pins on the Arduino. So a shift register is a good way of expanding the number of IOs we have available to us. And you can basically create a virtually unlimited number of IOs, and you only need 3 GPIO pins to do it. So we could connect all of these 40 LEDs just by using 3 pins. So let's look at that. To begin with, what I'll do though is I'll set up one of these modules, and I'll start by setting up the LEDs, and we'll connect them directly to the Arduino, and then later we'll insert the shift register and we'll just go from there. So the pattern we use is like this. So we use 8 LEDs. as I've tried to indicate here, we'll bridge 3 of them in the center across the center channel of the breadboard, and then we'll put some more laterally across the breadboard, so in parallel with the channel. So I'll show you how we do that. I'm going to use some 5mm LEDs. I'll use a combination of colors. Might be better if you just use one. It really doesn't make any difference. It's up to you. And there's the guide there. I will wire up this H indicator, but I won't be using it in this sequence, but it is used in the final project. Also, don't forget the 8 470 ohm or whatever resistors you're using to limit the current. You need one for each LED. So I find it easier to pick a side that I'm going to use for the ground. So this one is closest to the interior, so I'll use this side as the ground. So what that means is that all the short legs will go to this side. Now, to allow enough room for the shift register, which we'll add in here later on, I'll put it sort of close to the edge here. Now, as you can see from this, I've bridged it across the channel. So I'll put in a couple more like that. As you find that a 1 or a 2 hole gap between them is good enough. So I've left 2 holes between those. They can go 1 apart. I'll do 2 apart. And then this one will be my H register, which in the picture on the screen, I have it about there, but I'm going to put it over here, and I'll just leave a slightly larger gap. Okay, at this point it's probably easiest to put in the resistors, so I'll just put them in as well. Right, now, lastly, we'll put in the some other LEDs, which I've labelled as A, B, F, and G on this diagram here. So currently we have C, D, E, and H. Those labels will become meaningful a bit later on, but it's just a good way of identifying them. Now, for these ones, if we connect them up in this orientation, then that's not going to work. That's just a short circuit. So we actually need to connect them across a couple of channels like that. And so what I'm going to do is I'm going to insert these orange ones, which will be my lateral ones, so that it bridges the connector for these LEDs. So I'll insert it like that. Sorry, I don't need one there. So for consistency, I'm trying to put the cathodes on the left-hand side or this side. Might be the right side in the video. That's to make it a bit easier to connect the resistors up, which I'll do now. Actually, before I do that, hopefully you can see that these are bridging. It's a little bit hard to see, but they are. The orange ones do in fact bridge the column or the row that the red ones are connected to. Now you can see that for these 2 resistors here, I've stretched the link across to the blue channel. Again, for color coding sort of safety, it's good to make that the ground. So the blue one is always the ground. So they'll need to be a slightly wider extension for the legs, so it can go across there. But because I am using both sides, I will need to connect these up. Right, and that's it for our hookup of the LEDs. So you have a nice dice pattern here. And as I said, it looks segments are sort of connected up as per the diagram on the screen. Now the next thing that we want to do is connect them up to the Arduino. So I won't use the shift register just yet. I'll sort of illustrate the purpose of calling them A through H, and we'll try and get some patterns to come up on it. So this chart here, or this table here, shows the connections. Okay, so I place it like that, mostly because all of my anodes are mostly on this side, so it'll make it easier to connect up. But the first one I'll connect up is the ground. So it doesn't matter which side I plug it into it, but rather than reaching across the board, I'll just plug it into here like that, and then connect that up to the ground. And then as per the diagram, I'm going to say that this one is the A LED. So I'll connect that up to pin 2. So remember, that's going across the bridge from the red LED. So the A LED is, in this case, it's in column or row 3 on the breadboard. So that's to pin 2. Then the B LED will be this one. So again, that's bridging across the red LED. So that's in column 9 and on mine. That will be pin 3. Then the next one is LED C, which is this red one here, and that's in column 2 on this breadboard. So that goes over here to GPIO pin 4. And the next one, D, is this middle one. So that's in column 5, or row 5 on my breadboard, which also by coincidence goes into GPIO pin 5. Then this is the next one, so that's A, B, C, D, E. So that's coming underneath this orange one here, so it goes to this side of the orange one's connection, and that's pin 6, and that's row 8 on my board. And now we have to reach across to the other side, unfortunately. But there's no real way of avoiding that. So A, B, C, D, E, F. So that's coming in here. I think how can I do it? I think I'll put it around there like that. That's GPIO pin 7. Or maybe I'll just run it through the middle here. And then lastly, H. Okay, so just check the wiring. It looks like it's all okay. In pins 2 through 9. So yeah, that all looks okay. So we'll just give it a try to make sure, mostly that the LEDs are the correct way around, but also illustrate how we can sort of light things up to make a few dice patterns. Okay, so now that we've wired it up, let's see if we can get it to display something. So what I've done here is I've created a little table which is our font. So our font is basically a digital representation of some sort of image that's meaningful in some way for human readability. So we'd normally think of a font as the letters, but you also have fonts like Wingdings which have symbols and other styles. So this is effectively a font for our dice. And what we can do is we can digital write to each of the GPIO pins. So they're repeated down the bottom there. And depending upon which GPIO pins we write to and what we write to them, we'll create images on our dice. So for example, if I wanted to display a 3, I could turn on F, D, and B, which are those 3. Alternatively, I could turn on A, D, and G. It doesn't matter. That's the whole point of a font. You could do it however you want to. You could have it whichever style, leaning forwards or backwards. It's completely up to you. But that's the process that we'll use. And then these letters here, which I'm using now for simplicity, will become meaningful later when we look at the shift register. So let's have a go at doing that. Maybe we'll put a couple of them in. I certainly won't do all of them. The main thing is just to sort of test that I've oriented everything correctly. So yeah, I think we'll start a new one. So previously we've looked at this LED built in constant, and we've just sort of taken for granted that it's there and it has some meaning. So how do we create things like that? Well, I have previously used const, so we can do that. There's another way of doing it, and that's a so-called preprocessor macro, and I can define it like this. Why would I do it that way? I could equally do it like this. Both will have the same outcome. They do have slightly different properties, but they do, at least for the purpose that we're doing, they do work the same way. In fact, what I'll do is I'll do 3 like that, just to show that it can work. Note that there's no semicolon on the end of the hash define. What are we up to? C, D, H. Later, probably in the next video, because we'll need it more in the next video, I'll show you another way of using this macro to make some of our coding easy, particularly the dynamic sizes of the arrays. Would this be easier if I used an array? Maybe, maybe not. Okay, so what did we have? So we'll start out by writing the 6. So a 6 is G, F, E, C, B, and A. D is low. H is low. In fact, why not just leave that high, just so we can see it. Now we'll repeat this. This time I'll turn the H off. And so we'll output 3 now. So for 3, we would have A is low, B is high, C is low, D is high, E low, F high, and G low. And I'll just put another delay in here so we can see it. So with a little bit of luck, what should happen is we will certainly have tested all of the LEDs, because here we have D as low and here we have D as high, and we'll sort of see the different patterns. Okay, so I just upload that. Oh, it seems like once again it has to be plugged in for it to work better. Okay, so there's another Uno, so this is COM13, Uno is back. So select COM13, it's still an Arduino Uno, and upload. And there we have it. We have the 6 lit up with the H LED, and we have the 3, and it's alternating between those two. So I'll leave that at that point. It's up to you. If you want to try some of those other patterns, by all means, you can try replicating these, just copying and pasting and changing the settings and make it go through 1 through 6, or you could try doing an array implementation. But we'll move on from this and use the shift register, which is what I'll tackle next. Okay, so let's hook up the shift register. And as I've stated a few times, the reason we need that is because ultimately we're going to have 40 LEDs and 7 buttons, and there's just simply not enough pins on the Arduino to do that. So we're going to connect these shift register up. So this is a shift register. It's going to be hard to see it, but there's some numbers that are sort of printed on there. I doubt you'd be able to see that in the video. But the numbers sort of include, amongst other numbers and letters, just to make it a bit harder to sort of read, it says SN74HC595N. So the key numbers there are 74, 595. The HC, which is sort of in the middle there, describes the technology, and I think SN is the manufacturer. I've no idea what the N means. And then there's other production information that's on there. So they can be a little bit hard to read, but you sort of get used to it after a while. So I'll unplug that, and look at what the shift register is and how it works. So as you can see, I've got a diagram here of an integrated circuit. It's got the pins on it. And we can see that this one here, if you count them, has 8 pins on each side, so that's the 16 in total. You can also see on this one, there's a little notch here. There's a circle there, but that doesn't count. There's a little notch here, and there's also a little divot there. I don't know how clear that is. But that's to indicate the orientation, because if you just look at that, it's hard to tell which one is, according to that diagram, pin number 1 and pin number 2. There's no way of knowing. So that's what this little notch here is, and this little divot here is. I don't know what the hole there is. That's probably just for manufacturing. So if we were to hold it this way, then this would be pin number 1, and that's as per the diagram. So as we can see here, there's that notch. This one diagram doesn't show the little divot, but the notch is up like that, and so therefore pin 1 is in this relative position. And then they always number going down and around like that in a sort of anti-clockwise fashion. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now these symbols across the side tell you what the function is. And if we go to Google, Google has all of the best answers. Yeah, so Google always has the best answers. You'll be able to find all the information you want to need to know about the shift register in this so-called data sheet. And so there's a few sections of the document. I won't go through them, but this is a block diagram that sort of shows how it works. It shows how the inputs and the outputs relate to one another. So if I just quickly go back here, you'll see that we have QA, QB, QG, QH with a little prime next to it. There's RCLK and some other pins. So that they appear here in this block diagram. There's the QA, QB, there's a QH, and there's that's that QH prime. It's a little bit hard to see the prime, but there's definitely a prime there. And then there's these inputs, the SIR, SR, CLK, and so on. So in addition to showing you the inputs and the outputs and where they appear on the actual chip package itself, this diagram shows you how it works. And so the key takeaway here is that there's sort of two sides to it, and I'll mention this a few more times later on. But the way it works is that bits come in here through this SIR input, and then we sort of load them or register them with this SRCLK. And the SRCLK is kind of like a crank. It sort of turns the mechanism. And so what happens is the bit gets loaded in this first register, and we can see here this is the output, and so that goes the input to the next one. And so what happens each time you clock this register, a bit gets loaded here, the one that was here gets pushed down to here, the one that was here gets pushed down to here, and so on and so on and so on, until eventually it drops off at this QH prime, which is important for connecting them up. Now, the outputs aren't connected to these directly. They go through this sort of second half of it. And so what happens is we have a shift register part of it, which is where the data gets sort of shifted in bit by bit. And it's kind of like just sitting in there. Nothing's really happening to it other than this is remembering it. And that's where this clock comes in, the register clock. So when we toggle that, you can see that's connected to all of these. And so what happens is whatever is in these registers gets loaded up into this output register. And when it appears here, then it actually appears on the actual pin. So until we sort of clock this register clock, or the RCLK, or I'll call it the latch later on, nothing will happen on these outputs. We can shift in as much as we like, but it just sits there. It's only when we sort of tell it to, okay, now take this data that we've loaded up and send it out for display. And that's important because that can give us a very smooth display. We can sort of update a long chain, basically preload all of the data in here, and then once we're ready, we can just clock all of them to say, okay, now every single one of you take the data that's in here and put it on here for display, so we can get a very nice sort of refresh. This is a technique known as double buffering. Now a little bit further down, it shows you the packaging, and in fact it's this diagram that I, let's say, borrowed for the purpose of the video. and that's the one that's in the PowerPoint presentation, but it's also available in different formats. So this is like a surface mount or a much smaller component. It's in a more square orientation. I don't have one of those, but this is the one that I'll be using. And then there's more information. It tells you what the pins are and where they occur. There's some electrical information and a whole bunch of other stuff there that tells you its operating parameters. And then there's a timing diagram here that sort of shows how to work it. So I won't talk much about this other than to say it illustrates what I was describing above about how the shift register actually works internally. So how do we connect it up? Well, I purposely labelled these LEDs as A through H because that aligns with these QA, QB, which is the outputs to the shift register. So to wire it up, we just simply connect the A to the A, the B to the B, the C to the C, the D to the D, and so on, all the way through to the end. I'll put it in here. Just have to be a little bit careful when you put them in that the pins go into the holes. It's very easy to sort of fold them underneath, and you definitely don't want that. So it's a good idea just to have a little look at it and make sure that they are all going into the holes correctly, and that look down the barrel here to make sure none are folded under, which doesn't look like there are. So that looks like it's gone in successfully. So that's good enough. Which I think I'll orient it this way. Okay, so I'll start by wiring up the power connections, and I'll use these little wires that I made because these ones start to get a bit messy if you put too many over them. Again, because the notches here, this is pin 1, so that's 2, that's 3, that's 4, and so on all the way around. And then it's 8, 9, 9, 10, and all the way up to 16. So according to our diagram, VCC, which is the power, or plus voltage, goes to pin 16. So I just jump that across there like that, because this will ultimately be our power line. In fact, I'll just plug that in now before I forget. Right, so there's our power connected to 5 volts. What I might do is I might just bump that down to there like that. I don't need to connect the power on this side because I don't think I'm going to be using any power on this side. No. Now the next one I'll do is connect the ground, so that's pin number 8. So connecting pin 8 to the ground. Now the next one I'm going to connect up is this one, output enable. And so if we look at the output enable, which is the OE pin, we notice there's a little bar over the top of it. So that means it's negated. So what that means is that to enable the output, we have to send that a low. And the way we send it a low is by connecting to ground. Now we could connect it to a GPIO pin and do it that way, but I don't want to turn the output enable on or off, so I don't need it to be under the control of my program. So I'm just simply going to connect it to ground. So that's pin 13. So I've got 16, 15, 14, 13. So that's column 23 on my breadboard. So just double check that. 16, 15, 14, 13. So that's correct. And then the last sort of power one is the clear register. So that's this one, pin number 10, SRCLR. And again, that's got a bar over it. So to clear it, we send it a low signal. That's what clears it. So to not clear it, we want to send it a positive signal. And that's pin 10, which is the second last one here. So on mine, that's pin column 26 or row 26. So that should be good enough. So I've got pin 8, which is ground to ground. We've got pin 16 to plus V. We've got not clear to plus V because we don't want it to be clearing itself all of the time. and we have output enabled to low, which means that it is enabled. If we made that a high, then the output wouldn't be enabled and we'd never see anything. Okay, so the next step is to connect up the LEDs to it. So I'll simply reuse these wires coming out over here. LED A, that's this one. Yep. That would go to this pin here, which is pin 15, because that's where LED A is. Then the rest are basically in order down the other side of the chip. So the B LED, which is this one. In fact, I might just rip all of these wires out because that probably will make it easier rather than trying to untangle it. So this is the B. Then this. So there you go. I've made a mistake. So this one is this LED here, which connects to the second wire, is the A. So that goes to there. And then the B, which is this orange one here, goes to there. Then the C, which is this red one, which comes out underneath that orange one, is the next one. And then the D is the next one after that. Then the E, which is this red one, is the next one after that. Then the F, which is this one, is the next one. G. And lastly, H. Okay, so I'll just push those out of the way. And that's how it should be connected. So that's connected the LEDs up, but now we've got nothing connected to the Arduino, so that's a little bit of a problem. So how do we connect to the Arduino? Well, that's what these ones are all about. And we'll connect it to pin 12, 11 and 10. So basically like this. So I'll just connect those up quickly. I'll start with pin 10, which is going to be the purple connection. So pin 10 on the Arduino. So pin 10 on the Arduino will connect to pin 12 on the chip. So that's 16, 15, 14, 13, 12. So that's there. So pin 11 on the chip, which is the one next to the one we just connected, up goes to pin 12 on the Arduino. So that's this one. That's going to make the last one a little bit hard to plug in, but that's okay. And then finally the SER signal, that goes to pin 11 on the Arduino. So put that in there first. And that's pin 14 on the chip. Okay. So we've connected up all of those now. We haven't used this one here, which is the QH prime. When you connect up the next one, the QH prime from this one will become the SER on the next one. And the purple and the green ones will just follow through. They just basically connect up to all of them, so they all have the same purpose. Okay, so let's do a simple program to test this out. I'll just create a new program, save it. So I don't think we need this one anymore. The thing I'm going to do is create some variables or some constants that represent our connections to the shift register. So what I've done there is I'm defining obviously the pin that the register is connected to on the Arduino, but also what that connection is on the shift register. So as we can see from the diagram here, pin 12 being the green wire is used as the SR clock signal, the shift register clock, and that's connected to pin 11 on the chip. Now, if you wanted to, you could actually create the variables using these names or similar names. I find it easier to use these names because they're a bit more meaningful to me. So the data pin, that's the data value that I want to send to it. the clock pin is the one that we use to clock the thing to sort of turn the crank, as it were. And then finally the latch pin is the one that's used to load the data from the internal memory into the output buffer, which is what causes the contents to appear on this QA, QB, QC, and so on. Okay, the next thing I need to do is to set the I/O pins up. Obviously, they're all going to be outputs. I will cover this later on, but numbers in computers are stored in binary, so that's a series of ones and zeros. So what I'm going to do is just have a little counter that goes through and just basically counts from 0 up to 255, which is the maximum number of combinations you can have of ones and zeros with 8 of them, also 8 bits. And I'll just output that to the shift register. So what we'll see is sort of like an incremental pattern going on the LEDs as we progress. So there's that same for loop before. We're creating a variable image, and we'll start at 0, and then while it's less than 255, actually I can do less than or equal to, because I do want to output the 255, and I'll just increment it. So 255 will be every single one of these LEDs will be on. And then to send the data to it, we want to get ready to receive the content. So we'll set the latch pin to low. So this is just the rules. The data sheet will explain how this works, but we'll just look at the code now, and please just take it for granted that this is the way it works. You can certainly look this up by yourself. It also helps to spell it correctly. So this is where we output our image, so I'll come back to that. Now, the way the register works is when this latch pin goes from low to high, that's what causes the data to be transferred from the internal memory to this set of outputs. Now, just like Arduino provides helpful functions like digital write and pin mode and digital read and stuff like that, they also provide a helpful function for working with shift registers. And for fear of this not working again, which it probably won't, but we'll give it a try. Always be optimistic. And yes, it didn't work again. So if we go to documentation, and we go to programming, and then go to the language reference, then we should find somewhere here there it is, shift out. And so we can see the description of the function here. Again, I'll let you read this by yourself. But basically, we give it the two connections, the data pin and the clock pin, not the latch pin. That's something that we've done by ourselves. And then the value, which we want to output, which will be our image. And then finally, this bit order. And so then the bit order is MSBFIRST or LSBFIRST, and that's what it means. But what does that actually mean? Well, let's put it in first. So data pin. Okay. So we'll have it do it that way. Now I've chosen MSBFIRST. The other option was LSBFIRST. Okay, so for this program, it's not going to make much difference whether I use MSBFIRST or LSBFIRST. You can play with that yourself and just sort of see what effect it has. I'll use MSBFIRST because that's what I'm going to be using later on. And this will become more important later on when we start to define the font again for the shift register when we're displaying the dice images. But let's just give this a go first and see what it does. And of course, once again, it's better to have it plugged in. And so it looks like there's a bit of a problem. So what I forgot to do is actually allow some time for us to see what's going on. So we'll just try uploading this. Okay, so now you can see the patterns changing. And so if you look up binary values online, what you'll actually see is that this is showing as a 1, this is showing as a 2, this is showing as a 4. So what 3 would be 1 plus 2. What 4 is just that 1. Then what 5 is this 4 plus this 1. And then 6 is 4 plus 2. And that's why it's blinking like that. And these ones are sort of blinking fairly quickly as the count moves down the chain. So eventually you should see that all of them will light up as it gets to 255, which will be soon. And then it should reset back to all blank and then start off with 1, and then 2, then 3, then 4, and so on. So we're almost there. Here we go. Then it's blank. So 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay, so let's next make it do something a little bit more useful. And specifically what that will be is to display our dice images. So we'll set our dice up to work with this. Okay, so now that we've connected up the shift register and we've demonstrated that the LEDs seem to be working and all the connections are working, let's set up our font, and this time I'll do it properly. And so what I mean by doing it properly is meaning I'm going to set up a data set. So here's our font, which I've used before. And notice I had an extra line here because we do sometimes want to have a blank. It doesn't always just have to be the data that's set up, but since we're going to set this font up into a data set, we will need to have all of the images that we want to display. If we wanted to have an all on, so the 6 doesn't have them all on, then we would need to deal with that separately by having yet another element in here. So we can have as many or as few as we want in here, and we can label them in any way that we want. What I need to do is to convert this data from the lows and the highs that we initially used when we were digital writing to it to something that we can actually use that's a bit more like the shift out is accepting, where we just gave it a number, so that integer that was in this loop. So we need to give the shift out this image. And so an easy way of doing that is to just simply substitute each L and each H, or each low and each H, for a low or a high, being a 0 or a 1. And so we do that for all of those, and we get these values. Now we could go with these numbers as are. We could type them in like that. I feel that's just a bit too much typing, so I prefer to use a more convenient notation such as hexadecimal or decimal, and that's just a bit easier for us to type in. Now I prefer to use hexadecimal because once you become familiar with it, you sort of can work out and translate very easily that each of these groups of 4 binary digits is a hexadecimal number. So for example, I mentioned before about how these work. So this first one is counted as 1, this is 2, this is 4, and this is 8, and then we can sort of work out intermediate numbers by adding them together. So in this case I've got one lot of 2, so it's 22, so it's easy to translate. Here I've got a 1 and a 1, so that's a 2 plus a 1, so that's a 3. Here I've got a 4, a 2, and a 1, so 4 plus 2 plus 1 is 7. So it's easy to translate between binary and hexadecimal. Not so easy with decimal, but you can do it the same way. You just have to add up all of them, and I don't have one that's simple. Oh, here's one that's simple, so that's a 1, a 2, a 4, and that's an 8, so the decimal would be 8. This one would be a 1, a 2, a 4, an 8, then a 16, and then a 32. So 32 plus 2 is 34. So it's not quite as intuitive to translate between them like this one is, where I've got a 1 and a 2 and a 1 and a 2, so it's hexadecimal is 22. Now to make life a bit easier for you, I'll come back to this. You can do the calculation in most calculators, certainly ones that have a programmer or a base n function, and most do these days. So hexadecimal is base 16, binary is base 2, and decimal that we normally use is base 10. All of these representations are stored internally in the MCU in exactly the same way. These are just notations that make it easy for us and convenient for us to read and use. Right? So all of those options are just for our readability. And as I said, there's a calculator in Windows and most operating systems that allow you to convert it. So I'll just quickly look at that, and then we'll sort of code up our font. So once you start up the calculator, this is the sort of standard thing that comes with Windows 11, Windows 10 and earlier versions also had it, but the interface is slightly different. So when it comes up, you click on this little thingy here where it says standard, and then choose programmer. And then you get this sort of representation. It shows you the various modes that it supports. So bin, that's the binary. Dec, that's this decimal value. And then hex is the hexadecimal value. So I've entered in 6B, which is this number 5 here. And so we can see that's decimal 107. Check. And it's, well, that binary number there, which is that. So you can just type it in using the keypad, and that's just what I explained just now. Okay, so what we'll do is we'll encode our font as an array, and we'll use these values here. And what I also do is I'm going to reuse some of the code from a previous application, and I'll enable 2 buttons to enable us to go through these various fonts. Okay, so let's get started with that. I'll open up our challenge. So this is a good reason why it's good to do the challenges, because we'll reuse some of the stuff that's from the concepts that are from here. So I'll just assume that you know these. As you can see, I've switched over to this slightly bigger board. It's actually just 2 of these little ones. Also, I've made it a little bit tidier. I've put the connections on the one side. The other one I sort of did the wrong way around because they're just sort of jumping across there. It would have been better to have the LEDs around the other way like these ones are. And so then the wires are all on the one side rather than sort of blocking the image. Otherwise it's the same. And then the extra breadboard just has these 2 button pins, and these are connected exactly the same way as the challenge number 2, where we connect them to pins 2 and 3. And you'll note here that I do not have the pull-up resistor, so we'll get a peek into how we can avoid that. You might remember that I said we can do it another way, but we still need the resistor. We're just going to use one that's in here. So we'll start off with setting up the buttons. So I just simply copy, paste. Now, in this case, in the challenge, what we did was use the buttons to sort of step through these intervals. So I don't want to do that this time. I'll copy that just for simplicity. But instead of calling an interval index, I'm going to call it the image index. And again, we'll start at 0, because that's as good a place as any to start with. Okay, I think that's all we need for that. Not check blink. Sort of wishing I hadn't called them both check something now. So check button press. We definitely need to reuse that. Now the next thing I need to do is set the buttons for input. So that's not all of that, just this. Now this one won't work because this mode here assumes that we have the external input, external pull-up resistor, which I didn't include. So to enable the one that's built into the MCU, we use that. That's all the change that's required. So with that, what happens is, rather than expecting a resistor to be here as a pull-up resistor, it'll use one in here. Now, for these MCUs, there's no pull down resistor, so that's why I said it's better to use get familiar with the pull up, because pretty much all of the MCUs have a pull up resistor built in. Some have a pull down resistor built in. This one doesn't, so it's useful to become familiar with the pull up concept. Okay, and then the last thing we want to do is basically reuse this, but we don't want to do this loop, right? Because we're going to use the image index. And so this is basically the same as before. The only difference will be that if we look over here at the PowerPoint, I'm going to have 1, 2, 3, 4, 5, 6, 7 of them. So I'll call this one next, and I'll call this one previous. So if I click button 0, I want to go to the next one. So because we have 7 of them, that means it needs to be less than 7, because our indexes are going to be 0, 1, 2, 3, 4, 5, and 6. So we definitely don't want to go past that, but we want to get to 7. And of course, the variable is wrong. It's image index. Now this one's okay, because we definitely don't want to go below 0. So when it's 1, we'll allow it to go through, but when it's 0, then that's the end. But again, here, when we get to, we want to allow it to get to 6, but once it gets to 7, which is this one, we don't want it. Is that correct? So 0, 1, 2, 3, 4, 5, 6. So that should be 6. Right, because when it gets to 6, which is this blank one, we definitely don't want it to go further. Otherwise, effectively what will happen is we're just displaying random data. So you can try setting that to 7 and see what happens. You'll probably just see it's blank still, but it will effectively be random data. If you wanted to see actual random data, maybe change that one to -1, see what happens. Okay, so we've set our interval index, and now the last thing we want to do is output the image. Sorry, not the interval index, that's image index, isn't it? And that is going to be an array indexed by this this image index. So that'll be like that. So the last thing. Okay, so the last thing we'll do is declare our font. Actually, I'll make it const, because we're not going to change these values. They're going to be fixed. We don't need them to be negative. That's not going to be helpful. Image, actually, I might call it dice image, just to give it a meaningful name. And again, the array is open-ended. So we'll let the size be determined by the content that we put here. So dice image. And then simply all we need to do is include these values here. Now, I've created this earlier, so I'll just copy and paste it like that. So that's what we need to do. Now, if we wanted to use the binary values, the definition is just the same, except it would look like that. So there's the binary values. The 0B means binary, and then there's all of those. Now, we can't put spaces in there. That makes it easier to read, but they're not syntactically correct. Obviously, you wouldn't comment it out. I've just done that to make it easier. Or alternatively, we could actually use the decimal version by simply putting these numbers in place of these or these. But that should be enough. So let's compile it and give it a try. It's come up as COM3. So I'll upload him. Okay, and it looks like that's worked. We've just got this one LED on, so if we just check back at our code, our image index is 0, which is the digit 1, so that looks correct. I'm not sure which way this is, so we'll just see what happens. Press that one, nothing. Oh, there we go. So this side is up or next, and this side is down or previous. So I've pressed up. Now we've got those two lit up. So that's the 2. So I press them again. There's our 3, a 4, 5, 6, and then blank. And then nothing else should happen, and then go back 6, 5, 4, 3, 2, 1, and then nothing. And then of course the red one isn't used at this point, so that's not going to do anything for us. This one seems to be very weak, but I guess that's just the way it is. Okay, so I think I'll leave it there, but before I do that, let's have a look at this MSBFIRST thing. And before I go into that, another thing you could do is perhaps try adjusting the patterns. So, for example, our 3 uses this diagonal, as does our 2. Maybe try making it so the 3 and the 2 use that diagonal. Another thing, maybe make a little spinny pattern. So, like take the 3 and alternate it so that it lights up, what's that, D, B, D, and F. Then it switches to A, D, and G. And then C, D, and E, and then F, D, and B. So it makes us like a little spinny pattern or something like that, and try some other creative things. But now let's look at this MSBFIRST and LSBFIRST. So MSBFIRST is an acronym for Most Significant Bit First. And it's to do with how the shift register works, specifically that every data bit that we send to it will push down through this A, then the B, and the C. And that's to do with how it's wired up internally. So as you can see in this block diagram, the data, which is the SER, comes in here, and it appears in this block, which is eventually linked to the A output. And then as we bring in more data, it pushes down the line. And so the MSBFIRST is about which bit that we want to actually end up in the H down here. And if you prefer the timing diagram version of that, then that relates to this one here. So again, as we put our data in, it appears here in the A position, and then as we push more data in, courtesy of this clocking and the registration to the output, we can see it shifts down one by one. So the bottom line is that the piece of information, or the bit that we want to end up in the H, has to go in first, because it just cascades down and gets eventually pushed to this H bit. So we need to make sure that comes out first. And so that gets back to how we've wired it up, which is what I've shown here. So it really doesn't matter how you do that, as long as you have some consistency. And so what MSBFIRST means is output this one first. And because we output this one first, it'll initially appear in this A position. But as we output more, it'll get pushed down, so it'll ultimately end up in the H position. Now, why is it MSB, or most significant bit? Well, I've written these bit numbers down here, so traditionally the bits are written this way, and this is the least significant. So I did the arithmetic before, where I sort of looked at these and said that these are sort of powers of 2. Well, I didn't explain it that way. I said this had a weighting of 1, this was 2, 4, 8, 16, and 32. So if we take this 32, this one. Oh no, we can do this one. 32 plus 8 is 40, plus 2 is 42, so we get that decimal value 42. So this is the least significant bit. If I toggle this one, it just changes the value by 1. But if I toggle this one, it changes it by 128, so it has a much more significant effect. And also, it's the bit number 7, so that's the largest sort of position, and that's traditionally how we wired them. So when I say MSBFIRST, it outputs this one first, and then works its way down to here, and so therefore this one is what will end up in the H position. Of course, the opposite is LSBFIRST, and that just means it does it the other way, and I'll show a table shortly about that. And so that's just what I was explaining, that in order for this to work, we need to sort of have everything in sync and aligned, and so the way the shift register works is that the QH value must be output first, so that it can cascade down through A, B, C, D, and eventually end up in H. And obviously, conversely, the QA value must be output last. Hence, we go this way in that direction. If we change to LSB first, then effectively what will happen is, this is the same table, it's just the headings are more different colour and in reverse. So what would happen is this one would get output first, this one would be second, this one would be third, and so on. And so what will happen is this will effectively be the H bit. So you can try this in the code yourself, just change the M to an L. And what you'll see is that when you're in the 4th, 5th and 6th positions, then this H LED will be high. So when it's displaying 4, 5 and 6, we'll have this one lit up. And similarly, it'll affect all of the others. So for example, the 1, which is still the same value, so it's still 100 binary or 8 hex, so that's still the same value. But now the 1 will set the E bit. So that means the 1 should light up this LED, not this one. So again, it'll look a bit odd. But yeah, by all means, give that a try and see how you go with that. Hopefully that explains MSBFIRST and LSBFIRST and why that's important. Can you use LSBFIRST? Sure, maybe that's another challenge. You could rejig this table just by adjusting these values and then calculating the new binary and the hexadecimal values and make it so that it does output the correct image. So for example, number 1, we would light up D, so that would be this one would be set, which means this one would be set, and now the hex value would be 0x10. Okay, so what we've done here is we've basically built this little module here. And as you can see, this module is repeated through this larger circuit board. And then the wires that are coming into the shift register, which were those clock and the latch and the data, they're basically cascading through to each of the little modules. And that's how we connect them up. We've also sort of set these 2 buttons up, although we've used different functions here in the final project. That's like clear and roll, whereas here it's sort of like forward next, just for the purpose of testing it. But effectively, we've set these 2 buttons up. We just need to add the extra 5, so that's just the same logic, but they have different code behind them as to what they do. And so by having this goal, again, is sort of focus our learnings, and we're sort of gradually working towards this step by step. Yeah, so I've shown some optimizations again. So specifically how to encode the font and design it in a table and then encode that into our program. So we're sort of separating the data out from our code, and that will also make it much easier to send the images down to these subsequent ones. As opposed to the other method, which I sort of first did when we connected up the LEDs directly, where I had a whole bunch of digital writes. So you can imagine that that's going to get unwieldy very quickly when we're starting to have to deal with 40 dice, each having potentially 7 combinations if you count the blank. And also we have to turn the red one on as well. And so I sort of used some naming conventions to try and make life a bit easier. So if you remember from the first sample I did, I called those GPIO pins A through G because that then transcribed into the actual pin labels on the shift register. So that just helps make us follow the thought process as we go. So in lessons 1 and 2, I've covered everything you need to know to complete the project by yourself. The one exception is random number generation, but that's fairly straightforward. You can read about that at this link here. And then the final lesson, I'll add the random number generation and also some more things. So I'll show you how to daisy chain the 74 HC595 dice modules into that long chain so we can have multiple dice. I'll look at structures. So earlier I talked about arrays being like a 6-pack box of cans and a gift box sort of being maybe a can and a packet of chips or something like that. So a variety of things in one box. And so that's what a structure is. Again, that'll make life much easier, and that's actually an important stepping stone to C++ classes, which is a very powerful concept, even though I don't cover the C++ classes in this Patreon video. And then how to sort of expand our existing code to manage all of the buttons, and also have richer button management. So if you go back to the first video, I showed that when I press the roll dice and hold it down, it keeps rolling. So that's more than just a button click. So I produce a richer interface for the buttons. Again, you don't have to use that. You could follow a toggle process, so push it once to start and push it again to turn it off, which we did in the first video to toggle the LED off and on. But by having it sort of rolling for a little while longer after releasing the button, which the richer interface will allow you to do, you sort of get a much better a nicer sort of feel for it. And I'll also propose a couple of new challenges for you to extend the final project. So viewing the Patreon video is optional. You can definitely create the project by what's shown in videos 1 and 2. But as I said, going to Patreon supports me in creating more content like this and shows an interest. But maybe you don't want to create the dice game. Maybe you're happy with just using some buttons to control some LEDs in some other ways. For example, maybe you want to create a complex traffic light. So you could certainly use the techniques that I show in lessons 1 and 2 to create a traffic light project, for example, if that's what you wanted to do. So again, it's not required, but as I said, it does support me. So if you are leaving us here, thanks for watching. Let me know your thoughts in the comments. So I've looked at some strategies for learning that can be applied when you're getting started. So it really hopefully answers the, what do I do next after I sort of follow the tutorials in the starter kit. So we've learnt to enhance those programs, sort of combine them to use more things. We've used some techniques that make your life a little bit easier, such as structures and functions and constants, and again, skills that you can use to create my final project or some other project that you want to do. So again, if you're leaving us here, look for my other content and social media. You can find links and guides and stuff like that on my website. And as I said earlier, I also participate in Reddit on the r/Arduino forum quite a bit. So you might find me over there as well.
Okay, thanks for watching. I hope that was useful to you and taught you some techniques that you can use in your projects. Please leave a comment. I do like to read those, and also consider liking this video, subscribing to my channel, and then turn on notifications so you'll see new content when it's made available. And also look for me on social media, particularly Reddit or my website where there's a complete list of projects. You might also find my introduction to debugging video to be helpful. That's available on YouTube, and it's a follow-along guide which is helpful and teaches techniques to figure out what's going wrong when inevitably things go wrong. There's also a written version of that, and that's available in the wiki on Reddit in the r/Arduino subreddit. Okay, so once again, thanks for watching. All the best with your projects, and see you next time on All About Arduino.